Section 12.2 is double integrals over general regions. So now rather than integrating a function over a rectangle, we'll now integrate over any general region in the plane, or at least a general region which has reasonable boundaries defined by functions of y or functions of x. And see down below, general sketch of such a region D. And we want to find the integral of this lowercase f function, f of x, y, over D. And D is not necessarily a rectangle. Okay, but we will assume that D is bounded and contained in a rectangle R. So that's what's also drawn in this picture below, is that this region D is bounded, and we've picked out a rectangle R that does contain it. So we'll define a function so that way we can recast this problem, at least to start, in terms of an old problem from 12.1. In other words, recast it as a integrating over a rectangle problem. We'll redefine a function, capital F of x, y. It's based on lowercase f via the following. It's lowercase f of x, y for any point that's in D. So any point inside this region, it's just equal to lowercase f of x, y as expected. And it's 0 for any point that's not inside that rectangle. So now I have this anytime x, y is not inside, not the rectangle, but not inside the set D. Okay, but it is, however, inside that rectangle. Okay, so effectively, capital F takes on all the same values as lowercase f inside D, and outside of it, it gives 0 contribution. Okay, so that'll be useful in terms of calculating the volume above the region D in a moment. Okay, so we define the double integral of lowercase f over the general region D as being equal to the double integral of capital F over the rectangular region R, which contains D. Okay, F is defined as we have above. Now this recasts the problem on the right-hand side as the integral over a rectangular region, which means we have things like Fubini's theorem and whatever else available to us. Okay, of course we're going to want to generalize this or consider a more specific, I guess first we'll want to consider a more specific case of what one of these regions might look like. Okay, so here we've repeated what's in the box above. And the region we have here, D, we're assuming is bounded by a function g1 of x from above, g2 of x from below. And on the left and right hand side of the region, it just happens to be A and B. That's fine for this. And so really the region D that we're looking at is this region right here, roughly drawn out. We want to integrate the function f of x, y over this region. So the domain of the function is that set D right there. We want to find the volume, or at least integrate the function over this set D. Now, capital F is equal to lowercase f on all of this set D, and anywhere outside of it, but still inside the rectangle, it's equal to 0. Okay, so if we integrate capital F along this rectangle from A to B and C to D, A to B being the x value, C to D being the y values, then we'll be able to obtain the same amount of volume that's in this lowercase f over the region D, because capital F is 0 outside of that region D. So the last trick that we just don't see or aren't able to really get the details for, because it's just beyond the scope of the course, is the fact that we can change the limits of integration C and D to be from g2 of x to g1 of x. We might think about that as forming little cells in here that go up to as far as from g2 of x up to g1 of x, and then we integrate the volume over the top of that. Now, as long as this function g, or these two functions g1 and g2, are well behaved, continuous is a reasonable way to think about it. It's a sufficient condition for it. As long as g1 and g2 are continuous, we know that the following result holds. We can replace C and D with g1 and g2, or g2 and g1 respectively. And we've got what we see below in this theorem here. So now our limits of integration become functions of x. Okay, now there's a name for this type of region. So what we just saw, it's bounded by a and b and the x variable, but it's bounded by a function of x and another function of x for the y variable. So it's bounded above and below by a curve and then just straight vertical lines left and right. This is a region of type 1 or type 1 region. Okay, to integrate such a region, we'll split it up accordingly. Now let's note what's happening here in these limits of integration. This is dy, it's the inner integral. Its limits of integration go from g1 of x to g2 of x. So when we're done integrating this function with respect to y and applying the limits of integration, which are functions of x, we should be left with overall something that is entirely a function of x. Then we integrate with respect to x and apply the limits of integration from a to b and get a number. So that'll kind of guide us in the way these things should go together. Okay, so let's see an example. Evaluate the double integral over the given region, and our region D is a type 1 region. X ranges from 0 to 1. Those are vertical lines to cut off those boundaries, and the boundaries along the y-axis are 0 to x squared. Nothing that says we can't have still a rectangular boundary on one side. That's the 0. And now we have a non-rectangular boundary on the other side. Y has got to be less than or equal to x squared. So first things first, it's a good idea to get some, have a picture of what this region looks like or be confident about what we're integrating over. So x ranges from 0 to 1. So there's our borders on this side, our boundaries on this side of things. The 0 side seems a little less significant than the 1 on the right. Nonetheless, it's important to have it correct. Now, for y ranges from 0, and then it's bounded above, y is less than or equal to x squared. Well, here's the curve, y equals x squared. Our y values have to be below that curve. So that gives us the region D that we have described below. Okay, so this gives us a lower function, g of x, and a larger function, g of x, g1 of x and g2 of x, from lower to upper. Okay, we'll sometimes see too, if we're going to integrate in this orientation, we might see a symbol that looks something like this, sketched in the integral, or maybe somewhere tossed into the mix. And that looks kind of like a diode symbol. It's just a line with an arrow on it indicating that we're bounding our region, or we're thinking of the boundaries of our region as functions on either end of that arrowed line. From the least to the larger is the direction of the arrow. Okay, so putting this together, we have our integrand, no surprise there, y over x to the 5th plus 1. dA will be replaced by dy dx, or dx dy, depending on the type of region. For type 1, it's dy dx, because of course, this limit of integration should be functions of x. And they're exactly what we'd expect. We picked 0 for the bottom, x squared for the top, for the lower and upper boundaries. And we integrate this function with respect to y first. That gives us 1/2 y squared in the numerator. The denominator is constant with respect to y, so nothing happens there. Now we apply the limits of integration. Y equals 0 up to y equals x squared. So that's, well, our factor of 1/2 has been factored out to the front here. Now we have y equals x squared minus y equals 0 squared. So we get x to the 4th minus 0. That constant of 1/2 remains out front. And we now are left with this integral. It's a single variable, or it's a single integral and a single variable x. It's the kind of thing we want to see at this step. If there's still a y floating around, something's gone wrong. So, the wrong variable in here at this point, there's a mistake has occurred. So this is a prime candidate for a u substitution, and that's done off to the side. U is x to the 5th plus 1. We spotted that because x to the 4th is the derivative of x to the 5th plus 1, modulo a constant. It's that factor of 5 right there, but it's easily dealt with subbing things out. And once we're done handling that u substitution, applying our limits of integration like we normally would. Of course, we've changed them here because we have a u substitution. We don't have to do that. We could always come back to the variable x if we preferred. but at any rate, we've got them changed in this case. What we arrive at is 1/10 natural log of 2. So from about this point onward to the right and below, we're back to a standard Calc 2, Calc 1 situation. This is back to simply Calc 1, really, use substitutions. So that should be the case each time when we run through these. We should start with a double integral, carefully handle that situation, plugging in functions of x or functions of y, depending on the type of region we're dealing with, and arrive at a single variable integral, one integral, and be able to evaluate that in the traditional way, or the more conventional way that we're used to. Now, a region of type 2. This is bounded on the sides by curves. So now x is bounded by a function of y on the left and then another function of y on the right. Y is bounded above and below by horizontal lines. So just direct rectangular sides, and this are rectangular top and bottom lines for the region. So given an integral of this form, we sort of swap the roles of x and y. So we're going to integrate with respect to y first in this case. Actually, that is a typo. Glad I'm catching that here. Unfortunately, it's in the video, but that'll have to be, this should be dx first and then dy, because this is x equals this function h1 of y. That's the way to think about that, up to x equals the function h2 of y. Okay, so we integrate with respect to x first. Then what results will be a function which is in a single variable y. Okay, and that's exactly what we want, because we're going to integrate with respect to y and then apply those limits of integration. So let's see this happen in the example below. So we've got integrate over the region D, the function y squared dA. So the region D is -1 to 1 for y. So it's rectangular in the y coordinates, it's just constants. And then x is greater than the line -y minus 2 equals x, and it has to be less than or equal to y. So we sketched both of those lines. This is the line x equals -y minus 2, and the other one is the line x equals y. We found their intersection points by setting these two equations equal to each other. -y minus 2 equals y will yield this intersection point right here. So we know where that occurs on the graph. It's a good idea to have an idea where these things are. Now we realize the following. So here's our boundary of +1 for y. And then our boundary for -1 of y, again, doesn't seem as relevant, but we do want to keep ourselves from integrating something down here as well. That's not in the region. We're not interested in that. So it is cutting us off at this point as well. Okay. For the lower boundary to the left, or the lesser boundary to the left on the x-axis is this. So lesser is left on the x-axis, greater is off to the right. Okay, so we're going to integrate from the function or the line x equals -y minus 2 up to x equals y. And that's what we see here, -y minus 2 up to y. This is with respect to x, dx dy for the differentials in that integral. So with respect to x, y squared is a constant, so the integral of this is just y squared times x. And now we apply the limits of integration, x equals -y minus 2 up to x equals y. And what we get from that is y squared times all of this, and it's the upper limit minus the lower limit. And sorting out these terms, we see that we've got 2y cubed plus 2y squared from -1 to 1 dy. This is a single integral and a single variable. It's a polynomial. It's about as easy as it's going to get at this point. The result of that is 4/3. So that is type 2 regions. So bounded on the sides by curves and top and bottom by rectangular regions. Now, of course, it could be that a region is both type 1 and type 2. And I'll point that out when such a thing happens. Okay, in fact, it just happened. This is the type 1 and or type 2 region. It's bounded on the left and right by, it's bounded on the left by a curve and on the right by a curve. It's bounded above by a curve and below by 2 different curves. Okay, so the goal of this example, we're not given this graph right away, but I pointed out at least where we see a type 1 and type 2 situation. We're asked to set up the iterated integral for both orders of integration. So then determine which one is easier by inspection or maybe by carrying it out. We're just going to inspect the resulting integrals. So the type 2 region means that it's bounded on the sides. Okay, well, before we get there, let's of course note what D is. D is bounded by y equals x minus 2 and the parabola x equals y squared. So the parabola x equals y squared is this. It's opening sideways. The line y equals x minus 2 is this line. We found their points of intersection by setting both these y's equal to each other. So, well, first we squared this y to get x minus 2 squared and set that equal to the other y squared, which is just x. When we solve for x in this, we get the points 1 and 4 for the x values. Plug that back into either one of these curves, and we'll get what's down below, negative 1, 2 for our y values. So our coordinates are 1, negative 1, 4, 2. This is crucial because given which type of integral we decide to set up, or which way we decide to set our integrals up based on the types of regions we choose, we'll either need our x components, 1 to 4 in the x components, or negative 1 to 2 in the y components. So type 1, let's see, is that what we have first? First we have type 2 is what we set up. And that's because this just looks a little bit more obvious for type 2. Maybe with some practice, the viewer or the reader will see that. Type 2 is bounded on the right. The larger function is x equals y plus 2. The lesser function to the left, in all cases in this situation, in this region, is y equals x squared, or x equals y squared. X equals y plus 2 is the larger, x equals y squared is the lesser. Okay, so that gives us our limits of integration. Y squared to y plus 2 in such a region. Now we go back to what our integral was. Oh, we're integrating y. Okay, so that's showing up in the integral. For a type 2 region, we're going to vary along x from y squared up to y plus 2, as was pointed out from the graph off to the right. And the result of that, of course, would be a function in terms of y, which we would then integrate with respect to y and apply these limits of integration. Let's confirm those limits of integration for the y variable. Negative 1 here up to positive 2 for the y-axis, and that cuts us off, to keep us within this region and between these two curves as well. So negative 1 to 2 is correct for our integral along the y-axis for our dy differential. So this is the type 2, this is the integral for this region, calling it a type 2 region. Of course, it could also be considered a type 1 region. This is where we see that it's a bit more complicated. In the type 1 region situation, we're bounded here below by the curve y equals negative root x. We're bounded here by the curve, what is this going to be, y equals x minus 2. Okay, so then we'd have to split the region up then as 2 regions between here and here. Automatically, we see that this is going to be more complicated, but just to see that, how this is carried out, we'll do so. So, of course, in both cases, we're bounded by y equals the square root of x, positive square root of x, whereas the bottom here was y equals the negative square root of x. Okay, to get the lower half. So, in the type 1 situation, one integral will represent this portion from here to here. So x is going to range from 0 to 1. We're going to be bounded from negative root x to positive root x. That's exactly what we see reflected in the first integral. We're going negative root x to positive root x from 0 to 1 along the x-axis. And that handles the first integral. We need to add what we get from integrating over the second portion of the region. and that's here. And the lower function is y equals x minus 2 to the upper function is y equals root x. So x minus 2 to root x. And then, of course, our x values vary from 1 to 4. 1 to 4. So x is going to go from 1 to 4 for that interval. And I think that it's fairly obvious that only having to evaluate a single integral is preferred to evaluating two different integrals. So of course, the type 2 version is the easier situation. Now, of course, they both remain viable options. If we were to work our way down this path to some degree and realize we get to an integral that's just intractable, something that we're not able to find an explicit antiderivative for, then quite possibly we would consider this one just to see if we can figure it out. Even if it's longer and more work, we might not end up at an integral that we're stuck with. So the good news is, it gives you more options. The bad news is some of those options might look worse than others. Okay, more practice with these. Evaluate the double integral over the region D. So D is bounded by y equals x equals y cubed, and x is greater than or equal to 0. So or at least D is defined by this. So x is greater than or equal to 0 is the top half of the plane. So that handles that portion. X equals y cubed. That's the same as y equals cube root of x. That's this cubic function that passes through the point 1, 1 and the origin 0, 0. If we didn't know that, we could set x equal to x, and that would be y cubed equals y. That's y cubed minus y equals 0. We solve that equation for y, and we get y equals 0 or 1. Those are the two solutions, y equals 0 or 1. We plug that back into this to get the coordinate pair, 0, 0, 1, 1. If we needed to know all that, we didn't see that. See how to graph this at first. That's how you might go about doing it. But it's pretty easy to see with some practice and knowledge of these functions where their intersection points might be. Now that forms this region here. Without the cue for x being greater than or equal to 0, we might have actually included the region we just highlighted and another one down here, right? The problem doesn't intend us to do so, so it's good that we noted that that was the case. We're only integrating in this region. Of course, this is either type 1, up and down, bounded by curves, or type 2, left and right, bounded by curves. So it's either way, which is nice. We have a choice. Randomly, I've just chosen type 1, just arbitrarily. And type 1, again, is marked by up and down. Okay, so we're bounded on the top by x equals y cubed, or since it's type 1, we need to write that as a function of x. Y equals the cube root of x. So y equals the cube root of x here. In fact, I'll write that in so we have even more detail about it. Our upper boundary is y equals cube root x, and our lower boundary is y equals x. So that's what's occurring over here, x to cube root x. And that's along the y-axis. That's moving up and down the y-axis. And then integrating on the outer side for dx, we know that we're going from 0 to 1 for the region between these two curves. And that gives us 0 to 1 here. So just to follow through on the new part of this, we find the antiderivative with respect to y here. We get x squared y plus 2y is antiderivative is y squared. Now, from applying the limits of integration for that integral, we go from x to the 1/3. And that results in this. A little bit of algebra brings us to this expression in our integrand. Now this is a single variable integral, single integral of a single variable function with respect to x here, with real number limits of integration. And you can carry out the details of that on your own as the viewer or reader and get 19/60. So that's it for that practice. And finding the volume of the solid under the plane x minus 2y plus z equals 1, and above the region bounded by x plus 1, y equals 1, and x squared plus y equals 1. So it has to find the volume formed by these this space here, by this surface or this plane above that region. Okay, typically this will be finding the volume of a solid formed by some three-dimensional curve here, some three-dimensional curve or surface rather, and then some region in the plane. Maybe it's the cap of a sphere, or it could be a paraboloid or ellipsoid or whatever else. Now, handling this problem, we want to get an idea of what the region is. That's all we really need to graph. If they tell us the plane is above this, and we're finding the volume underneath it, we just take it for granted that it is in fact above the XY plane in this given region. And that's sufficient. That's fine for these problems. We're not going to make it any harder than that. Now, the region is y equals 1 minus x. So we've graphed this line here. Okay. The other boundary of the region is y equals 1 minus x squared. That's a parabola opening downward. We can find the points of intersection by equating y's to each other. So then y minus x equals 1 minus x, 1 minus x equals 1 minus x squared. Solving for x, we'd see that we have the points 0, 1 and 1, 0. If we needed that, or otherwise we just graph it or know from intuition or just knowing these functions well. Our region is enclosed in here, and we have a choice once again. We can go type 2 this way or type 1 vertically. Again, if one integral looks worse than the other, we might try one method versus the other one. In this case, type 1 was arbitrarily chosen, indicated here, up and down. So we're bounded on top by 1 minus x squared, bounded on the bottom by 1 minus x in the region. From left to right, we're bounded by x equals 0 to x equals 1. That's reflected in the limits of integration, x equals 0 to x equals 1 for that integral. And from here, we proceed as usual. Integrate this function with respect to y. This is a constant, so it's this constant times y. This integrates to y squared, and we apply the limits of integration. 1 minus x to 1 minus x squared. So carefully laying these things in here. This is 1 minus x, this is our constant here, times y at 1 minus x squared minus y at 1 minus x. So we've just handled all of this for both limits of integration. Now the other portion of this is the y squared term, and that's this term at this function minus this term at this function. So square this function and then square this function as the right-hand side of the difference there. And this, once we're done collecting all the terms and organizing things, is again a single integral in a single variable x with real number limits of integration. And what we come out to in the end of this, being careful, is 37 over 60. Okay, so yeah, once we've handled the double integral part of this and the careful aspect of setting this up and then evaluating at the limits of integration and carefully placing those things, we're back to Calc 1 most of the time and just integrating a pretty standard definite integral. So one thing I would recommend with any one of these problems, try to graph the region. Don't try to graph the volume of the solid or anything like this. Don't graph functions of 3 variables. Graph the functions of 2 variables. All you need to understand is the region. The integral works out the rest of it for you. Okay, it's just like the solids of revolution back in Calc 2. You didn't always have to draw the solids of revolution, but it was good to draw the region that you were going to revolve, and then you could decipher everything from there for the most part, at least everything you practically needed to get it. Okay, this section finishes up with some properties of double integrals. These 2 properties here are the linearity of these double integrals. So for type 1 or type 2, this also carries over. We can split up the sum, the integral of a sum, as the sum of the integrals, the double integrals. Okay, we can factor a constant out of a double integral to be a constant times the double integral. If a function f is greater than or equal to a function g for an entire region D, then the integral of that function is greater than or equal to the integral of the lesser function, or double integrals for everything I've said so far. Another one, if D is equal to D1 union D2, it's comprised of two different regions, D1 and D2, and D1 and D2 have no overlap. A picture would look something like this maybe. We'll draw a region in red here, and then we'll say that maybe D1 is this upper region, D2 is the lower region. They have no overlap. They're not crossing each other over. Then we could split the integral along those regions. If that's necessary, then we'll certainly do that. Well, it actually, in fact, was necessary in the example which asked us to find which type was easier to integrate over. We, in fact, split our region that we were given D into a left region and a right region based on where the lower border or the lower boundary of that region was. So that was us using that rule, sort of tacitly assuming it to be the case. And we see here that it's official, it really is a fact. Now, one of my favorites in all of this is we can use the constant function f of xy equals 1 to calculate the area of a region of integration. So if we were interested in finding the area of a region D, right? So ignore the fact that I've made it a three-dimensional object. Just look at that upper portion of it and just say that that is D. It has area A. That, we haven't calculated yet. That's the region D. Now, if we set the function f of xy equal to 1, and we integrate that constant function of 1 over the region D, we're going to end up with A of D, which is the area of D. Okay? Now think about it this way. If we knew the area of this solid, say it was some lamina, right? Some small, flat, sheet-like object. Okay? If we knew its area, and then we measured, it had a little thickness to it, and we measured that thickness and it was equal to 1. Well, then the volume of this solid D, or this solidified version of D, would be the area times its depth, to give it a cubic dimension, and it would still be A, right? Its volume and area would be equal in magnitude or quantity. The units would be different. One is squared, one is cubed, but the number is still the same. That's exactly what this thing is telling us, what this rule says. So we can use these double integrals if we want to go back and calculate any areas we want for any regions D. That could be useful. That might confound things and make them worse for some of these problems, but we might see that show up in a couple examples or exercises. Then lastly, if a function f of x, y, two variables, is bounded on the left by lowercase m and on the right by capital M for all ordered pairs x, y, and d, then we use this area of D function from above, but we know that the function then, using that area, is less than or equal to m times the area of D, and, greater than or equal to the lowercase m times the area of D, and it's less than or equal to capital M times the area of D. This should look familiar. It's somewhat like, it is very much like, it's the analog of m times b minus a is less than or equal to a to b f of x dx less than or equal to capital M b minus a for a function of a single variable. Okay, b minus a is the measurement of the interval. In this case, a of d is the measurement of this region D. It's the area of it. In this case, we measure the length of an interval. Here we measure the area of a region. Okay, so that's the analog of an old bound that we've had since Calc 1 for functions of single variables. And that's it for section 12.2. These problems are going to be quite a bit more tricky than 12.1. Navigating, setting up the regions is one of the hardest part, and then being very careful with the way you evaluate the first integral and apply those function limits of integration that are showing up. So be sure to take your time there, practice a lot of problems with this, and 12.3 we'll be looking at integrals over integrals in polar coordinates. So